Hi, everybody. I'm Alessandro Cheli from the University of Pisa, and this is Philip Zucker from Boston. And today we'll be talking about a new package that we are developing for Julia, Metatheory.jl, that allows us to do metaprogramming using equational rules, and this is why it's called algebraic metaprogramming. So let's introduce Metatheory.jl. Metatheory.jl is a package for the Julia language with a metaprogramming library, and it takes advantage of two major things. The first one is the awesome Julia capability of reflection and homoiconicity. And the other capability and the other thing that we are using is called eGraph. It's a data structure from theorem provers from the 80s, and a new algorithm from 2011, which is called equality saturation. And if you measure the two together, you can do a lot of cool stuff. For example, symbolic mathematics, abstract interpretation, equational reasoning. And yeah, the most important thing is that we are using equational reasoning for many cool tasks, and most importantly, optimization tasks. So you can read more about Metatheory.jl, a short introduction, in the paper we published on the Journal of Open Source Software, or you can also check out the repository up down there at the link. And so what can we do with Metatheory.jl? So we can do a lot of cool things. The main mechanism is general purpose term rewriting through equational rules on any Julia type. And with this, we can do, for example, high-level compiler transforms on expressions, flexible symbolic mathematics, or custom code optimizers still using equational theories. Or in the future, we can also work on optimizing deep learning models for flux. And we can also do some theorem proving using some theorem proving techniques and algorithms. Or we could also use more experimentally symbolic regression or floating point error fixers for the compiler. I leave the word to Philip, which is going to introduce the data structure.
So a starting point for why you might be interested in Metatheory.jl is that equations are good. In science and engineering and in my scientific education, a lot of the paper and pencil manipulations that I've done can be thought of as manipulating equations. So there's many applications from different domains that can be thought of in an equational way. In engineering and physics, you have ordinary algebraic expressions like plus, times, cosine, exponential, and you have equalities like cosine squared plus sine squared equals 1. Or you can think of integrals and derivatives in an equational way. Or you can think of doing matrix and vector algebra calculations in an equational way. Or you can think of doing quantum mechanical calculations using commutators and operators in an equational way. In pure mathematics, algebraic structures such as groups also involve equational calculations. Or in category theory, some of the calculations in category theory can be thought of as equational calculations. And beyond that, even in computer science, there are many applications of equations. Stream fusion can be thought of this way, which is an optimization where you want to remove intermediate loops and remove intermediate data structures in a transformation pipeline. Or compiler optimizations can be thought of in this way, finding a faster way of computing some number, let's say. Or in query optimization, which is finding a fast way to query a database. So the standard sort of classical approach to approaching dealing with equations in a computer, as exemplified by systems like Mathematica, Maxima, SymPy, and Symbolics.jl, is first off, we take these paper and pencil things and we think of them as trees, as a data structure in your computer. And then what you do is you take the equations and you think of them, you orient them into rewrite rules. So a rewrite rule has a pattern left-hand side and an instantiated right-hand side. And what you do is you search through the tree for the right-hand sides, you instantiate the right-hand side using the bound variables, and then you typically destructively update the tree with the new right-hand side. Okay, so in doing this, equations are oriented maybe unnaturally in one direction. You're turning an equation, which is a bidirectional concept, into a rewrite rule, which is sort of a unidirectional concept. Now, some rules are obviously good as simplifications, if simplification is what you're trying to do. So cosine squared plus sine squared equals 1, that's a pretty good rewrite rule. It's really reducing the size of the term. So most of the time, you're going to want to write that left to right. But the systems that do this, you have to pick a controlled order, or they just apply the rules in an arbitrary order. And it turns out that it's not always a good order, the thing it ends up doing. You can end up in local minima, or you can end up in loops. So some rewriting systems have good properties, and those rewriting systems are called confluent and terminating. Confluent means that no matter which order in which you apply your rules, you end up at the same result. And terminating means that eventually the rules stop applying. Eventually, you can't find left-hand side patterns anymore, and you're done. Now, if that's true, that's great. But that is more the exception than the rule. So what do we do about non-obviously oriented equations? For example, the associativity of addition is really a vital reasoning step in algebraic manipulations. And should we go that from left to right, right to left? If we have both, we're just going to end up in a loop. It's not clear what to do. So one solution to this problem was presented in the egg work, which is an egraph implementation in Rust, and a paper describing some very interesting twists on the egraph data structure. So the egraph it is a different representation than the tree, a slightly different representation. And what it does is it represents many terms as a pile of E nodes and E classes, okay? And you can see in this picture, the solid line boxes are what's known as E nodes, which contains the symbols, the sort of nodes of the tree that you are familiar with. And then there's also these dashed lines, which are E classes, equivalence classes. And these are intermediate nodes in the tree that are known to be equivalent to each other, okay? Now, I sort of have a little story that I want to tell about how you can go from the classical rewriting picture to the egraph data structure that I hope will help explain a little more what that previous slide was showing. Okay, so we said that the problem is when you take a classical rewrite rule and you do it in the typical destructive way, you're losing information. You're going one way and you can't necessarily go back, and maybe you make a bad choice. Okay, so, well, a simple method with which to avoid this problem is instead apply non-destructive rules, copy everything. Okay, so that's great. Then you maintain a set of all the possible trees that you can get to using your rewrite rules. And conceptually, the egraph is a fast data structure for holding this set of trees, holding and analyzing this set of trees. Now, there's two essential things you can note, observations you can make. There's significant sharing in what you're doing. When you make these if you bulk copied everything from a tree every time you apply the rewrite rule, this set would be absolutely massive. But you can notice that, for example, if you have a big tree and you're applying the rewrite rule sort of at the top, it's really going to be sort of permuting these big subtrees. It's going to be swapping them around to make the new tree. So instead of copying all those subtrees over to the new tree, you can instead use sharing. So you can just point to the original subtrees that you're reusing. Okay, so that's optimization one. And observation two is that if, for example, if you had a big tree and you're applying a rewrite rule sort of at the bottom, now there's not shared subtrees, but there's sort of significant shared unchanged parent structure up here, okay? And a mechanism by which you can have sharing of these parents is to introduce these equivalence class nodes. So instead of directly going to a subtree, you go to an equivalence class node, which then points to all the things that are known to be equal to each other. Okay, so then you can share all the big superstructure above that point. And then what you end up with is that this data structure is a bipartite graph of E nodes and E classes. And the two algorithmic / data structure techniques that are very useful for implementing this data structure in a fast and efficient way are the union find data structure and hashcons data structure, which in turn sort of implement the equivalence class sharing and the subtree sharing. So why is it interesting to do this thing that's already pretty great in Rust in Julia? I don't think I need to belabor the point too much. If you're already here, you're already very excited about Julia. But Julia is high level, easy to learn, it's performant. It has excellent Lisp-like metaprogramming and reflective capabilities, has an excellent high-level dynamic type system, supports generation and manipulation of programs as first-class values. And the thing that really gets me going is that it has an excellent scientific and engineering package ecosystem that we can really combine with Metatheory to do fantastic things. So here's a quick sketch of the data structure, a much simplified data structure of the egraph in Julia. So we have here the E nodes, which I said hold the things like plus, times, and variables. And that would go into that symbol field, the head field. And then the arguments point to all the equivalence classes that are the children of that E node. And then the E class is a set of E nodes that are known to be equivalent to each other. And finally, the E graph weaves those two together, actually has them talking to each other. With a memoization table, which is the hashcons data structure, a dictionary pointing from E-class IDs to E-classes themselves, and the union find data structure, which is that int disjoint set, which allows you to do fast equational reasoning. So the basic algorithm with which you use this egraph is you're given a starting egraph G that you insert a term of interest into, something maybe you're trying to simplify, a set of rewrite rules T, and an iteration limit N. So for each rule in T, you still have a pattern left-hand side and an instantiated right-hand side. And you search through the egraph for the pattern left-hand sides. For each match produced, you instantiate the right-hand side, and you apply the rewrite. But the difference here from the classical rewriting approach is that instead of destructively changing the egraph and losing information, instead you just assert that there is this new term that is equal to the old term that was the found pattern left-hand side. So you're never losing information. Then you do a bottom-up traversal of the graph to rebuild what's called the congruence closure. And this is inferring new inequality information for you in a very useful way. Now, if the egraph hasn't changed from the last iteration, it's saturated, and you can just say you're done. But in general, it won't. But that's not a problem, because every time you find a new thing to insert into the egraph, and you know when you're inserting new things, you're gaining information and you're making progress. So even if this thing runs forever, it's still always making progress, whereas the classical rewriting system might just be doing the same loop over and over and over and over again. But in general, you might want to have an iteration limit N that stops at a certain point and just gives you the best thing. Maybe you can pull the best term you've been able to find out of the graph at that point. Now, knowing if an expression with a set of rules saturates an egraph or never terminates, it's actually still an open research question. So that's an interesting side note.
Okay, so going ahead, what is so cool about egraphs? What is so cool about this data structure? So we say that classical rewriting has got some problems. For example, it requires a lot of user reasoning for defining the strategy and the ordering of rules. In the compiler community, when to apply each rewrite is called the phase ordering problem. So which phase should we order first and which phase should we order after? And so how do we solve that? Do we apply all rewrites simultaneously? Do we keep the history of all the rewrites? That's going to require exponential space and exponential time. So it requires a lot of user reasoning to do this fast. How do we do that? How do we manage this? So if we take equality saturation and egraphs together, we get egraph rewriting, which is the cool, new, exciting technique. And it solves the phase ordering problem, and it gives you bidirectional equational rules for free because we solve the problem of having rewrite loops. Here's an example rewrite system that we want to simplify a term. So we import the Metatheory module, we import the Metatheory classic rewriting module, we initialize the system, then we define a theory with the theory macro. A theory is just an array of rules, and this is a simple macro for doing it in an easy way. So you can see that we have rules that go from the left-hand side to the right-hand side, and the symbols are called pattern variables. So they're like universally quantified variables. If you're familiar with pattern matching, you're familiar with those kind of variables. So we have a rule that says that A plus A makes 2A, and that's okay. And then we have the commutativity rule. But if we see that A and B are universally quantified, we can see easily that this rule is going to cause a loop, because we go from A plus B to B plus A, and then we go back again because we will match the same variables. And the last rule is a simple simplification rule. We take out the 0 from the addition. And so if we use a classical naive strategy, that rule is never going to be applied, because we're going to try to apply the first two rules again and again and again. So we show an example with egraph rewriting in the next slide. So at the top, we have a simple rewriting system, the one I showed now, and we have a simple expression, x plus 0, and it's never going to terminate because we are never going to commute 0 plus x and going ahead to search for the next rule, so the simplification rule. So it will be the same result as the starting expression. So using egraph rewriting with equality saturation, this problem is avoided. So we avoid the problem completely, and we get the result we expected, solving the phase ordering problem. And going ahead, we are going to show some examples of Metatheory.jl and some use cases where we use Metatheory. So the first one, and most exciting and important one, is the integration of Metatheory.jl with Symbolics.jl, the new computer algebra system developed by the MIT guys and the Julia community. So Metatheory.jl can be used to rewrite any Julia expression, any Julia symbolic expression, and also Symbolics.jl expressions. So this has proved really useful for optimization. We develop a set of equality rules that you can see there. It's really simple. It's just 3 rules and a cost function to generate equivalent expressions that are computed in less CPU cycles. So computing the solution numerically, computing the value of an expression numerically is going to be much, much faster with less CPU cycles. Now we tested it against a big ODE model of human B-cell antigen signaling chemical reaction networks. We simplified the terms, and we showed that the simplified terms take half of the time to run the simulation. So that's very important, because if you're running a big simulation using modeling toolkit or Symbolics or whatever you want, halving the time is a big improvement. So instead of 2 hours, your simulation can take just 1 hour if you optimize it before with Metatheory.jl. And we published this result in a paper, which is going to be published at ISSAC, the conference about symbolic mathematics. Going ahead, how does the pipeline work? It's really simple. The pipeline for the user is really simple. We take a Symbolics.jl expression, we transform it into an E-graph, and then we apply the equality saturation with the set of equations, and we saturate the E-graph. So we add information, we add equivalencies, we get many equivalent expressions. And then with the cost function, which tries to find the expression with less CPU cycles required to compute, we extract the most optimal expression. And how does it work? How do you turn a Symbolics.jl expression into an E-graph? We are developing a new package called terminterface.jl, which is going to be a shared interface between many packages that implement and provide symbolic expression types for interoperation between those packages. So if you implement those simple methods, they are probably going to change in the future, but you just have to implement a set of few simple methods to make your symbolic type, your custom symbolic type, supported by Metatheory.jl and many other packages we're planning to develop. And going ahead, we're going to show another simple example that shows a property of E-graphs, an experimental result we figured out. So with SymbolicUtils, if we'd like to compute the Fibonacci sequence, the classical Fibonacci number, we do the naive recursive definition, and that takes a lot of time. It takes, it's not the best solution for computing the Fibonacci sequence, but that's just an example. With SymbolicUtils, you can see that we are defining the set of rules, and we are also defining the strategy. So we are chaining the rules together with a postwalk, so that depth first search, and then a fixed point operator to repeat the search again. And that's a strategy. While with Metatheory.jl, we define the set of rules, a slightly different syntax, and then we also define the function for extracting the solution. And you can see that we are not defining a strategy, but we're giving 2 parameters. A big timeout, because we do not want this to stop before it's got the solution. And we also define the scheduler. So we pass the simple scheduler because we do not want any optimization. We want to apply all the rules all the times. And we extract the shortest expression out of the 3. And how comparing those 2 solutions, what have we found out? We found out that using an E-graph for computation, we can see in the plot in the next slide, using an E-graph for the computation, we memorize the solution. So it's something that basically comes over from dynamic programming, and the results of the past computation are stored in the E-graph. So it takes much less time to compute the solution compared to SymbolicUtils.jl. And that's called implicit memorization of computation. And going ahead, I leave the word to Philip.
So another interesting possible application of meta theory is for category theory calculations. So category theory is an interesting and powerful abstraction that can be applied to many different domains. And Julia has a really fascinating package called catlab.jl, which is encoding category theory concepts and trying to use them in a computational way. And so the idea, the basic idea here is that we want CatLab and Metatheory to be able to talk to each other to some useful end. And it seems like it makes a lot of sense because, for example, CatLab has axiom sets encoded in it already that are basically equational axiom sets. Now, CatLab is based around the logical framework called generalized algebraic theories, which presents a little bit of difficulty in how you encode them to an E-graph. And what makes them a little bit different from algebraic expressions you might be used to is that there's both equational reasoning happening on types and terms. And that's useful in a category theory context because there's interesting equations that apply to objects, which are part of the types of morphisms. So we've been experimenting with different possible encodings of GATs to Julia, and some are slow and some seem to do a little bit better. And so here's one possible encoding that I describe in the blog post linked to at the bottom. And it's based on the idea of guard and E matching. So this is a category theory equation, although you could think of it as a matrix equation. And if you look at it and think about it, you actually note that this equation only applies when the dimensionalities of matrices are correct, when they actually line up in a way for this equation to apply. So this is sort of a general thing that happens, that you sort of need the objects in a category theory equation to line up for the equation to actually apply. And so the idea is to use guards to only fire these rules when the objects are in the appropriate configuration. And then as part of that, you need to internalize type derivations into the eGraph and into the rewriting rule system. Is this the right way to go? I don't know, but it does seem promising at the moment. So there are two applications of this that are very interesting: simplifying categorical expressions and also proving categorical theorems, equational theorems. And a very interesting future direction that metatheory can go is outputting human readable proofs that it finds of these equational proofs.
Okay, so the last example I'm going to show is a comparison with the Knuth-Bendix algorithm for a simple group theory problem that Marek Kaluba, a mathematician, suggested me from the Julia community. So is an expression equal to the identity element in a group? We consider a particular kind of groups called Hurwitz groups of type 2, 3, 7, and n, where n is a parameter. And we develop a set of rules. You can see we have the basic group theory rules. It's strictly non-commutative. And then we have an expression, and we want to show if the expression is equal to the identity element. We build the rules by hand. We also have a new function that repeats the application of an operator. So it's literally, you can see the last two rules are a times b applied, for example, 7 times, or a times b times a times b capital applied to itself, multiplied to itself 12 times symbolically. And then what have you shown with this? We have shown that Knuth-Bendix.jl, Marek Kaluba's implementation of the Knuth-Bendix algorithm, fails on big N parameters. And while Metatheory.jl, it takes 40 milliseconds to solve this problem. So we would love to investigate more about the Knuth-Bendix beating power of eGraphs rewriting. So some other examples that we have with Metatheory.jl, you can find them in the test folder. We have some example of partial evaluation of lambda calculus. We have propositional logic solving because term rewriting is Turing complete. And since term rewriting is Turing complete, we also have an interpreter of an imperative language, a simple example toy language. We have also developed a super interpreter. So it's an interpreter that memoizes with the properties shown before in the Fibonacci example. It memoizes all the computations. So it's an interpreter that if you give it the result, it can go back to the starting program that codes the computation. And that's a really cool thing to investigate. So final words, what are the future directions for Metatheory.jl? As I said before, we're looking for a more stable interface package for interoperability between symbolic packages defining custom symbolic types. We're looking for faster pattern matching because right now we are using a virtual machine, and we're looking towards using some relational algebra techniques for pattern matching. Then we're looking for smarter algorithms for more efficient saturation. So smarter optimization, trimming down the space of rules and when to apply those rules to make the library faster. And then we're also looking for a very important thing. So human readable and machine verifiable proofs of equality. And that's going to be very important for category theory and other use cases. Oliver Flatt is working on this on his PhD. And then we are also looking for better debugging and logging utilities because at the current state, Metatheory.jl is working, but you're going to be lucky when you are debugging a set of rules. It's really hard to figure out what was the rule that caused a failure, why and when. So we're looking for better logging, and probably also interactive logging will be really cool. And some other use cases we're planning to test and work on. So the first one is exciting. It's array symbolics with Symbolics.jl. The Shashi and the other guys are working on this right now. And we're also looking towards optimizing the Julia IR. So we're experimenting with Metatheory.jl at the compiler level. And we're also looking forward to optimize deep learning models for Flux, and also for optimizing quantum circuits using some category theoretical ideas for Yao.jl and the new IR that Chen Cao is developing for Yao.jl. So thank you everybody for listening to the talk. I hope you appreciated our introduction to Metatheory.jl, and I hope you're gonna enjoy the package. Bye.